When astronomers announce the discovery of a habitable exoplanet, the public immediately imagines a lush green world. But we are actually finding bizarre eyeball planets locked in permanent global ice, featuring only a single localized liquid ocean. Instead of orbiting gentle, stable suns, we are watching violent red dwarf stars physically blast the atmospheres off their inner terrestrial worlds, leaving behind nothing but sterile, irradiated rocks. And as the James Webb Space Telescope returns complex new spectra, we are discovering that active star flares can create fake chemical signals, tricking our instruments into seeing atmospheric water that isn't even there. The scientific definition of a habitable world simply means a rocky planet orbiting perfectly within the Goldilocks zone. This is the exact orbital distance from a host star where equilibrium temperatures allow liquid water to theoretically pool on the surface. To meet NASA's strictly defined institutional baseline, a planet merely needs this mathematical potential for water, alongside an available energy source and basic elemental building blocks like carbon and nitrogen. It absolutely does not mean that biology currently exists there, and it certainly does not mean a human being could survive the landing. An astronomically habitable planet could easily feature crushing surface gravity or a toxic, high-pressure atmosphere of pure carbon dioxide. To filter the massive, growing catalog of known exoplanets, researchers heavily rely on the Earth Similarity Index, or ESI. This mathematical scale ranks planets from 0 to 1 based strictly on their physical radius, bulk density, escape velocity, and estimated surface temperature. However, the Earth Similarity Index possesses a massive observational blind spot. Because we have historically lacked the instruments to measure exact chemical compositions from afar, the index completely ignores atmospheric toxicity. A planet scoring near a perfect 1 could still instantly kill you. We also have to enforce a strict terrestrial constraint. To even be considered a habitable candidate, a world must be rocky, generally sitting between 0.5 and 1.5 times the physical radius of Earth. Any planetary body larger than that threshold possesses too much gravity. It will rapidly accrete surrounding hydrogen and helium gas during its formation, inevitably becoming an uninhabitable mini-Neptune completely devoid of a solid, accessible surface. For decades, this mathematical, gravity-based framework was all we had to work with. We found planets in the right orbital bands, calculated their estimated masses, and simply assumed that some of them must have maintained a secondary atmosphere through internal geological outgassing. But that early baseline assumption is currently undergoing a brutal reality check. Between 2024 and early 2026, the James Webb Space Telescope has utilized its MIRI and NIRSPEC instruments to gather empirical, mid-infrared spectroscopic data directly from these distant terrestrial worlds. This monumental transition from theoretical modeling directly into observational science has shattered many of our early astronomical assumptions. JWST data is conclusively proving that simply existing in the Goldilocks zone is vastly insufficient to secure an atmosphere. We are finally realizing that if a planet lacks a strong global magnetic field or sufficient planetary mass, extreme stellar winds will simply strip its atmosphere away. Without an atmospheric blanket to distribute the heat, any surface water rapidly boils off into space or freezes completely solid. Now that we know habitable strictly guarantees nothing more than the physical potential for a puddle of water, we have to look at the extreme worlds that actually occupy this zone. And the most common habitable candidates orbit stars completely unlike our own sun. And the most common habitable candidates orbit stars completely unlike our own sun. Our galaxy is overwhelmingly dominated by M dwarfs, commonly known as red dwarfs. According to transit surveys from the Kepler and TESS missions, these small, dim stars host the vast majority of our rocky planetary candidates. But there is a severe geometric catch to orbiting a red dwarf. Because these stars burn at a fraction of our sun's temperature, a planet must orbit extremely close just to stay warm. Their habitable zones are pulled in so remarkably tight that the orbital dynamics radically change. When a terrestrial planet orbits that close to its host star, the stellar gravity exerts an uneven pull across the planet's diameter. This tidal force creates immense internal friction, acting as a planetary brake that slows the world's rotation over millions of years. Eventually, the planet's spin synchronizes perfectly with its orbital period. This mechanism is known as tidal locking. Just as our moon always shows the exact same cratered face to Earth, these exoplanets are permanently anchored into a single orientation with their star. This physical configuration completely dismantles the myth of an Earth-like day and night cycle. One hemisphere is subjected to eternal, unyielding daylight, while the far hemisphere is plunged into a permanent, frozen night. There is no rotation to distribute the incoming solar energy. If you were standing on the substellar point of the day side, the massive red sun would simply hang motionless in the sky, never setting for billions of years. This extreme static temperature gradient shatters our traditional global climate models. On the dark side, the planet is entirely deprived of stellar radiation. Temperatures plummet so low that researchers map out scenarios where the atmosphere itself could condense and freeze out onto the surface, leaving the entire world locked in solid ice. Meanwhile, the day side is constantly baked by the star. If the planet possesses enough water, it will not form the global circulating oceans we are familiar with. Instead, the global ice shell only melts directly beneath the star, where the heat is most concentrated. This orbital geometry creates what planetary scientists formally refer to as an eyeball planet.
Viewed from a distance, the world features a global crust of white ice, pierced by a single circular liquid ocean that eternally stares back at its host star. The exact climate boundaries depend on atmospheric density. Modern climate models suggest that a thick enough atmosphere might circulate heat toward the night side, potentially creating a habitable terminator zone, a ring of permanent twilight where the ice gives way to liquid water. While we cannot visually image these surface oceans, the tidal locking itself is not a guess. It is a strict dynamic consequence of the tight orbital intervals recorded by TESS, meaning almost every Earth-sized candidate we find is subjected to this extreme orbital constraint. Statistically, this is what the Goldilocks zone actually looks like. The most common habitable real estate in the universe is not a rotating globe of continents and seas. It is a locked, bifurcated world defined by a localized iris of water. Because these locked worlds sit exactly where water should be liquid, they fueled immense optimism in early astrobiology models. Researchers initially assumed that as long as the temperature was mathematically correct, these planets would naturally maintain their environments. But an eyeball planet is permanently changed to a volatile star, staring down the barrel of its solar weather. And the crucial question becomes, does existing in the right geometric orbit actually protect a planet from being stripped bare? To understand the current crisis in exoplanet science, we have to look back at the optimistic assumptions that guided the last decade of research. For years, we thought orbital geometry was enough. In the early 2010s, the baseline working model for habitability relied heavily on thermal equilibrium. Researchers even developed the Earth Similarity Index, a mathematical scale that ranked exoplanets largely on radius, density, and this expected equilibrium surface temperature. The traditional Goldilocks zone was defined almost entirely by stellar irradiance.
If a rocky planet sat at the exact right distance, the theory went, the star would warm it just enough to keep water liquid without boiling it completely away. But temperature alone cannot support a liquid ocean. You absolutely need a thick layer of atmospheric pressure. To solve this, early climate models assumed these distant rocky worlds would naturally behave exactly like our own. They relied on a continuous mechanism called geological outgassing. The idea was that active planetary volcanoes would constantly vent carbon dioxide and water vapor from the deep interior, continuously replenishing the atmosphere and replacing whatever leaked into space. It was presented as a neat, unbreakable theoretical balance. The planet's gravity would confidently hold on to the heavier gases, while the thermal energy radiating from the star wasn't supposed to be strong enough to give those molecules escape velocity. Because Earth and Venus were our only true terrestrial reference points at the time, this became the astronomical standard. Researchers largely assumed these habitable zone exoplanets would successfully hold on to thick, stable, and potentially life-supporting atmospheric envelopes. But this early thermal equilibrium picture had a massive, fundamental blind spot. It relied almost entirely on the atmospheric physics of planets orbiting relatively quiet, stable yellow dwarf stars exactly like our own sun. As we just established, the vast majority of our new habitable candidates actually orbit red dwarfs. And these M-dwarf stars are violently active, frequently unleashing extreme ultraviolet radiation that behaves nothing like the steady heat source our early models expected. While some early papers did predict extreme atmospheric stripping around these volatile stars, those warnings were often marginalized. The sheer public and scientific excitement of discovering the first Earth-sized candidates in the right orbital band simply drowned out the pessimistic math. The exoplanet community essentially made a collective bet. Researchers hoped that a combination of strong planetary magnetic fields and heavy, continuous geological outgassing would be enough to keep these alien atmospheres intact, despite the relentless stellar abuse. And this optimistic, Earth-centric paradigm held strong for the better part of a decade. It survived because we only had the mathematical equations to work with, completely lacking the precise spectroscopic instruments needed to actually read the chemistry of these distant worlds. To be clear, thermal equilibrium is still the required first step for any habitable world, even if it is not the final determining factor. But our assumption that a protective atmosphere would automatically survive the journey was about to be severely tested. This theoretical confidence held until the James Webb Space Telescope finally pointed its mirrors at the most famous habitable zone system in the galaxy. When it looked for the thick atmospheres we assumed were there, the data revealed a much harsher reality. The optimism of the last decade has collided with the harsh empirical data of the James Webb Space Telescope. We finally have the instruments to look directly at the planets we thought were safe, and the observations have forced a massive correction. The problem lies with the host stars themselves. Red dwarfs might be the most common stars in the galaxy, but they are notoriously violent. They subject their surrounding planets to intense ultraviolet radiation and frequent coronal mass ejections. Unlike our relatively calm sun, active red dwarfs produce massive stellar winds. Magnetohydrodynamic models have long suggested that these outbursts could easily overcome a planet's gravitational hold, physically stripping away its atmosphere within the first billion years of its life. But models are just math until they are verified by observation. That verification arrived when JWST pointed its mid-infrared instrument, or MIRI, at the most famous habitable zone system ever discovered, TRAPPIST-1. Astronomers mapped the thermal emission of the inner three planets, TRAPPIST-1b, 1c, and 1d. If these worlds had thick, protective atmospheres, the heat from the star would be redistributed globally, significantly lowering their dayside temperatures. Instead, the MIRI data returned a flat thermal emission spectrum. TRAPPIST-1b showed a blistering dayside temperature of roughly 500 Kelvin, with virtually no heat moving to the night side. It is the exact thermal signature of a completely bare rock. TRAPPIST-1c and 1d followed the same grim pattern. The thick, carbon dioxide-rich atmospheres we once assumed would naturally form through geological outgassing were completely absent. The violent stellar winds had likely blown them into deep space eons ago. There are still alternative interpretations. It is physically possible that these planets possess extremely thin, clear atmospheres of heavy gases, like pure oxygen, which JWST's current resolution cannot easily detect against the glare of the star. It also remains uncertain whether these worlds could outgas secondary atmospheres much later in their evolution, long after the host star finally calms down. But right now, the empirical evidence points heavily toward barren rock for the inner system.
This does not mean the entire TRAPPIST-1 system is dead. The outer planets, particularly TRAPPIST-1e, sit further from the worst of the radiation and remain viable targets for ongoing transmission spectroscopy campaigns. And even stripped bare, these inner worlds are scientifically invaluable. They are definitively terrestrial planets, providing perfect laboratories for astronomers to test and refine our mathematical models of atmospheric loss. But the Red Dwarf Dilemma creates a severe bottleneck for the search for life. If the most common stars in the universe systematically destroy the atmospheres of their closest planets, the true number of habitable worlds drops dramatically. To find a real atmosphere, a planet needs a structural advantage. It must either be massive enough to generate the gravity required to hold its gas tight, or it must be positioned perfectly outside the star's most destructive reach. With the inner TRAPPIST-1 planets confirming our worst fears about atmospheric stripping, the astronomical community has pivoted. We are no longer just looking for a rock in the right orbit. We are looking for a world that can actually hold on to its ocean. Despite the brutal realities of red dwarf stars, the search has yielded a compelling survivor. As of early 2026, one specific exoplanet has emerged as the strongest candidate for a true habitable water world. That planet is the super-Earth LHS 1140b. Located 48 light-years away in the constellation Cetus, LHS 1140b sits precisely in the safe zone for liquid water. But unlike the barren rocks we've observed recently, this world possesses enough mass and gravity to fight back against the stellar winds of its host star. This combination of mass and orbital distance is exactly what astronomers have been hunting for. And in March 2026, the Royal Astronomical Society published a landmark catalog identifying the top 45 rocky targets for immediate biosignature searches. Led by researchers like Abigail Boll, this study, nicknamed the Project Hail Mary Catalog, ranked LHS 1140b as the premier target. The justification comes directly from recent James Webb Space Telescope data, specifically using transit spectroscopy to measure the planet's density and atmospheric profile. The JWST readings provided the first strong empirical hints of a nitrogen-rich atmosphere, fundamentally similar to the protective envelope around Earth. This is a critical threshold because without that atmospheric pressure, any surface water would instantly boil away or freeze solid into the void. But the most striking revelation from the telescope data is the sheer volume of water this planet likely contains. Density models suggest that 10 to 20% of the total mass of LHS 1140b is made of water. To put that into perspective, our own Earth is mostly dry rock. Water makes up less than 0.1% of Earth's mass. This super-Earth contains exponentially more water than our entire planet, making it a true water world by structural definition. However,
You should not picture a global undulating ocean like you would see in a science fiction movie. Because LHS 1140b is tidally locked to its star, the distribution of that massive water content is highly localized. The planet is most likely a frozen snowball, trapped in permanent ice on its dark side.
But directly facing the star, at the substellar point, the temperature reaches a comfortable 20 degrees Celsius, melting a massive, permanent liquid pool. Global climate and phase curve modeling estimate that this liquid iris is roughly 4,000 kilometers in diameter. It is an eyeball ocean almost the size of the Atlantic, staring unblinkingly at its red dwarf sun. As confident as the current data appears, there is still a boundary of uncertainty. The exact depth and chemical composition of that liquid ocean remain beyond our current observational limits, and a competing interpretation of the data still exists. Some astronomers caution that the low density of LHS 1140b could theoretically be caused by a thick envelope of hydrogen and helium gas. If deeper transmission spectra detect a massive hydrogen signature in the future, it would mean this is an uninhabitable mini-Neptune, not a rocky water world. Yet, even if it lacks surface water, its verified density proves it is fundamentally different from the dry, sterile rocks found in the inner TRAPPIST-1 system. LHS 1140b represents our most successful observational victory to date. It looks incredibly promising in the data, standing as the ultimate test case for habitability. But there is a massive observational trap hidden in this exact type of measurement. What if the atmospheric signals we are reading aren't coming from the planet at all? That question sits at the center of a major observational dispute known as stellar contamination, or the transit light source effect. It is the single biggest reason why astronomers hesitate to declare victory on atmospheric detections. When the James Webb Space Telescope stares at a distant habitable zone, it does not actually see the planet. It only sees the host star. As the planet passes in front of its sun, a tiny fraction of that starlight filters through the planet's atmospheric limb. If gases like water vapor or methane are present in that atmosphere, they will absorb specific wavelengths of light. This leaves a distinct chemical fingerprint in the transmission spectrum that reaches our detectors here on Earth. Under theoretical conditions, this method is practically flawless, but the vast majority of our habitable targets orbit red dwarfs, and these small stars are notoriously chaotic. Their surfaces are turbulent, frequently covered in massive, intense star spots and magnetic active regions that constantly shift. These star spots are significantly cooler than the rest of the stellar photosphere. In fact, they can be cold enough for simple molecules, including water vapor, to temporarily form directly on the surface of the star itself. This creates a geometrical trap for our instruments. If a completely barren, airless planet transits across the bright, clean equator of the star, it leaves the cool, water-rich star spots near the poles entirely unocculted or unblocked by the planet's physical shadow. Because the telescope collects all the light from the system into a single pixel, the starlight skimming the sterile planet is seamlessly blended with the light radiating from those unocculted star spots. In the final spectroscopic data, the baseline spectrum is profoundly altered. The chemical fingerprint of the star spot is imprinted onto the transit signal, perfectly faking the presence of a deep, water-rich atmosphere on what is actually a transiting dead rock. By early 2026, radiative transfer models demonstrated that this false positive biosignature can be an order of magnitude stronger than a genuine planetary signal. A sterile rock passing a spotted star produces the exact same data graph as an ocean world passing a clean star. This optical illusion is precisely what happened with several of our most heavily scrutinized targets.
Recent analysis of the TRAPPIST-1 inner planets, which once showed tantalizing spectroscopic hints of atmospheres, conclusively revealed that those signals were likely just noise shaped by the host star. The planetary bodies themselves, like TRAPPIST-1c, are almost certainly completely barren, airless rocks. The telescope is working perfectly, and its spectroscopy is incredibly precise, but the universe is proving to be far noisier than our early planetary models anticipated. Some researchers argue that careful baseline monitoring of the star can entirely subtract this noise, preserving the planet's true signal. By mapping the stellar surface variations over time, we can theoretically isolate the planetary atmosphere. But doing this correctly requires mapping the exact temperature distribution and spatial location of star spots on a target that is dozens of light years away, in real time. It is an exceedingly difficult computational challenge that leaves many promising detections locked in dispute.
The one thing that remains absolutely true is the physical size and orbital mechanics of the planet. Those measurements remain accurate regardless of stellar surface noise. But this contamination means we cannot blindly trust single observations of atmospheric gases. It forces us to question every promising graph we receive. If the observational data is this muddy and the host stars are this deceptive, what can we actually say for certain about the habitable zone today? Amidst all the false positives in stellar noise, it might seem like we are back to square one in the search for life. But the astronomical community has not retreated. Instead, they've drawn a new, much stricter map of exactly where to look. For decades, the Goldilocks zone was a blunt instrument, based mostly on simple one-dimensional calculations of starlight hitting a rock. Today, researchers have replaced that broad brush with rigorous atmospheric circulation models to define what is now called the 3D habitable zone. These advanced models account for complex planetary heat tolerance, predicting exactly how a tidally locked world circulates warmth from its permanent day side to its frozen night side. By applying these physics, scientists can immediately rule out planets destined for a runaway greenhouse effect. The impact of this modeling is laid out in the 2026 Project Hail Mary catalog, published by Bull and colleagues in the monthly notices of the Royal Astronomical Society. They applied these strict three-dimensional limits to known exoplanets, aggressively filtering the observational data. The result is a dramatic reduction. Out of thousands of candidates, the 3D habitable zone leaves us with a highly restricted list of just 24 prime targets. This is not a failure of discovery. It is a precise sharpening of our scientific crosshairs. Even if atmospheric signals are currently masked by stellar contamination, we know several undeniable facts about these 24 survivors. We know their exact locations, their precise mass, and crucial transit data confirms they are definitively terrestrial rocky bodies. The crown jewels of this refined list include TRAPPIST-1e and HLS-1140b. Both are structurally confirmed and perfectly positioned within this new three-dimensional framework. There is no longer any doubt that they possess the physical bulk required to host liquid water. This model has also forced a strategic pivot. Because innermost planets are heavily vulnerable to being stripped by red dwarf flares, the search focus has shifted outward. Observation strategies now prioritize slightly more distant, cooler worlds over their heavily bombarded inner siblings. However, a major layer of uncertainty remains. Being in the 3D habitable zone guarantees the right physical placement, but we still cannot guarantee that any of these 24 restricted targets actually possess an atmosphere today. They could easily be sterile, dead rocks. There is also a risk that these models are too conservative. Because they rely heavily on Earth-like physics and known atmospheric chemistries, it is entirely possible they are missing habitable conditions on planets that utilize exotic, alternative greenhouse mechanisms.
The ultimate test of these models would be an outlier discovery. Finding definitive proof of a liquid ocean on a planet located entirely outside these newly defined parameters would force us to rethink the math, proving life's requirements are broader than we thought. Yet, right now, this restricted catalog represents the highest quality target list in astronomical history. We are no longer wasting telescope time on planets mathematically doomed to boil or freeze. We have the right targets, and we know exactly what is confusing our instruments. The final barrier to confirming a true alien ocean is the host star itself.
The violent magnetic storms of these red dwarfs are still throwing up a wall of false signals, preventing the James Webb Space Telescope from getting a clean, uncontaminated read. We cannot simply keep staring at these exoplanets and hoping this stellar noise clears up on its own. If we want to prove these 24 worlds have atmospheres, we have to find a way to finally filter out the star and see the planet clearly. If we want to prove any of these top exoplanet candidates actually have atmospheres, we have to find a way to finally filter out the star and see the planet clearly. We can no longer rely on educated guesses or models that assume a quiet host star. To break this observational deadlock, astronomers are deploying a dedicated instrument designed to look at the star and the planet at the exact same time. It is a deceptively simple solution to the most complex problem in astrobiology today. This is the NASA Pandora mission, a specialized smallsat that launched into low Earth orbit on January 11, 2026. Instead of trying to build a larger mirror to gather more light, Pandora was built to gather two specific types of light simultaneously. Pandora is explicitly designed to solve the stellar contamination crisis. It is currently observing at least 20 known exoplanetary systems, staring at them for long, continuous stretches to map the volatile behavior of their host red dwarfs. The mechanism relies on a dual instrument strategy. A visible light photometer continuously monitors the host star, tracking the dark, turbulent star spots and violent flares that create the false atmospheric signals in our data. At the exact same time, a near-infrared spectrograph reads the planetary transit as the world passes in front of the star. By having a perfect, real-time map of the star's visible activity, scientists can mathematically subtract that stellar noise from the infrared planetary signal. Once that stellar contamination is cleanly removed, whatever infrared signal remains belongs entirely to the planet. This technique allows us to unmask the true nature of these worlds, separating a barren rock from a genuine eyeball planet holding a liquid ocean. Pandora acts as a crucial pathfinder, cleaning up the noisy data so that larger observatories like the James Webb Space Telescope know exactly where to focus their immensely valuable time. It prevents us from chasing mirages created by stellar flares. However, Pandora does have strict physical limitations. It uses a highly compact 45-centimeter telescope, which restricts its capability to only the brightest host stars and the largest planetary signals in our catalog. Because of its small aperture, it cannot analyze the faintest, most distant Earth-sized worlds on its own. If the stellar noise proves to be completely random and mathematically impossible to cleanly subtract, even Pandora's dual-band data will not save our current atmospheric models. There are competing strategies to solve this problem from the ground. Next-generation extremely large telescopes, currently under construction, might bypass the noise entirely by using high-dispersion spectroscopy to pull the planetary signal out of the stellar glare. But regardless of whether ground-based observatories or orbital smallsats win the race, the Pandora mission is providing the most detailed, continuous map of red dwarf stellar activity ever recorded. Even if it finds no atmospheres, it fundamentally changes our understanding of these violent stars. The definition of habitability has shifted from a theoretical orbital zone to a grueling test of survival against stellar radiation. We are no longer just looking for a rock in the right place. We are looking for a rock strong enough to hold on to its sky. As Pandora gathers its final data this year, we are closer than ever to a definitive answer. When the stellar noise is finally cleared away, we will know which of these alien worlds is just a sterile stone and which one is looking back at us with a true liquid ocean.